Okay, so this problem right here, as I'm getting logged in, this is a probability distribution for a random variable. Okay, we don't know exactly how many cars are going to be sold in a given week, but we know how many we expect, or we can calculate that at least. So remember, the easiest way of doing that, we can just take each of the numbers and the probability and multiply them together, add it all up. So I could do 0 times 0.32 plus 1 times 0.28 plus, and so on down the line. And, you might find personally that that's a faster way of doing it for you. You might find it's easy just to put this into list 1 and list 2 and do your one variable stats using list 2 as your frequency list. And I did that earlier. I believe it's 1.53. So I'm just going to go to one variable stats. The expected value is 1.53. So I'll just put expected value of this random variable. So of course, that's not the answer, and that's not even an answer choice. But now we want to take this and we can transform this by multiplying it by whatever the actual profit is. So if it costs 21,000 and we sell it for 24,500, the profit is $3,500 per car. Okay, and if we're going to sell, we expect to sell 1.53, just multiply those together. So 3,500 times 1.53 is, there it is, 5,355. And that's all there is to it. So if you kind of forgot the steps for that, hopefully there's a reminder there. Expected value. Okay, so we're going to start with our progress, everyone's favorite part, and then we're going to be looking at just conceptually a bunch of stuff from chapter 20. And if this stuff does not make sense completely for you today, it is definitely something we're going to be doing over and over and over again. So really just introducing some concepts today, and we're going to proceed from there. But let's see where we've made it so far. Oh, look at that. We made it all the way to Havasu Canyon. And just in case, I think I've said this before, but just so you know where we're headed, we're just making it to Separation Canyon. That's where we're going to finish all of our new content. This last little float is just a review. This is all nice and calm down here anyway. So we're getting through all the hard stuff. You can see where we're going, I mean, metaphorically. And this is where we are, but let's take a look at this. This is why you come to class. All right, we got a nice big old canyon. Look at that waterfall. Look at that beautiful blue water. All right, some of you might have been here before, bringing back some memories. I've never been here, so it's bringing up some future memories for me if I ever make it down there. All right, we're not going to spend too long with it, but nice scene from the canyon. Now let me go back to here. Okay, so we've got an activity to start us off with today. A local engineering firm had to conduct a series of layoffs recently. They will lay off 10 people. The company has 180 employees that could be laid off. All are equally qualified, so the company decides to use a lottery system to be carried out by the manager to decide who will be laid off. The manager posts a list of the employees to be laid off. 5 employees are women, 5 are men. One of the women claims this is gender discrimination and starts a lawsuit against the company. The manager responds, how could there be gender discrimination when half of the employees laid off are female and half are male? What additional information do we need to evaluate this statement?
You need the amount of men, they're the proportion of men and the proportion of women in the 180 employees.
Perfect. You guys got it. I'm sure a lot of you were thinking the same thought, so that's going to go a long way toward determining if this is discrimination or not. So I'll go ahead and give that information to you. 60 of the 180 are women. So I'll just put F for female. And that means 120 of the 180 are male. Okay, so there we go. Now we know those numbers, and before we move ahead, you can just, if you want to share anything, you can. If you just want to think about it for a second, knowing this, do you feel like discrimination is happening? I'll just pause there for a second for you to think. And as you're thinking through it, that's kind of the idea here behind what we're doing. This is hypothesis testing, and we'll of course get into that more formally later. But the idea is we might have an initial thought like, oh, I wonder if this is discrimination. I wonder if it's not. And we have in statistics come up with some methods to work through this to determine if it is something, not in this particular case, well, in this particular case it's discrimination, but in any case where we're seeing an actual result that happened versus what we might have expected based on the probabilities, we might look at it and say, is that something that could have just happened by random chance? Or is that something that maybe it wasn't a fair process and they were discriminating and they decided to pick some females and they didn't really do it with a lottery system? So that's kind of what we're going to be jumping into. So this is how we're going to get started. We want to set up a simulation. So can anyone think of a way of setting up a simulation to investigate the gender discrimination claim?
You could maybe take a random sample of 10 employees and see how many are male and how many are female.
That sounds great. There you go. And we're not in our simulation right here. We could consider that this random sample that you're talking about, this is the group of people who are randomly selected to be fired. And that's, I'm sure what you're saying, I'm just clarifying. So yeah, so if we had a random sample of 10 pulled from this population, how many times would, or what kind of proportions would we get? So how would we simulate a random sample of 10?
You could like write all of the employees' names on like slips of paper and put them all in a hat and just like randomly grab them.
Absolutely, that does work. Of course, we're not going to do that. That's labor intensive for us to write down, but we that is a very legitimate way of doing it. You're absolutely right. What's another way of doing it that's kind of fast for us?
You could give each of the employees a number 1 through 80 and then generate 10 random numbers.
There we go. Yeah, and that's kind of the approach that we're going to take to it. And there's lots of different ways of doing this. So Zach, you said one. Matt, you just threw out one. You could come up with other ways. You could do rolling dice. You could do spinners. You could do drawing cubes from, like, if you had different color cubes and drawing them from a cup. So many different ways of setting up a simulation, but we will use a random number generator. And so we're going to assume that all of the women, so the females and males, what numbers could be assigned to the females? So I'm going to give you a hint right here. We got 180 employees. So I want to have a random number generated from 1 to 180. What might we use as a range for the females?
1 through 60.
There you go. So let's say 1 to 60 would be female, meaning 61 to 180 would be male. Okay, if we select 10 numbers, all right, so I will, if we run this 10 times, then we'll get some kind of proportion. So we're going to have 10 people picked, and we're going to have some number out of 10 which are female, and that would be our proportion. So what I want you guys to do, and you can do this easily a couple of times if you want to go and do this like 3 or 4 times. It doesn't take long once you get started, but let's set up a random number generator on our calculator. In case you forgot how to do that, you have to go to the math button, over to probability, down to random integer, and I'm going to do 1 to 180. Now I'll tell you, I'm not going to be a huge stickler for if there's repeats or not. Technically, we shouldn't. So if you wanted to do random integer no repeats from 1 to 180 and just look at the first 10, that's a possibility too. But I'll just do random integer 1 to 180, and I'm going to draw random numbers. If it's somewhere between 1 and 60, that's a female, and I'm going to keep track of the number of females and males that I get. And I'm going to go through this, so I can do this like a few times, and we'll keep track of what proportions we get. Does that make sense to everyone? Okay, so I see some of you are already working on that. So take a few minutes to get that down and keep track of your results. So I actually ran through this 5 times, did 5 different simulations of 10 trials each time. You didn't have to do that many. So what I'm going to do is I'm going to add my 5 results, and I got some pretty strange results. I mean, not all strange. So I got 0.2, 0.3, 0.4, 0.6, and I got 0.8, which is, I think, pretty unusual. So this is the proportion of females that were laid off in each of your simulations. So I'll let you go ahead and fill in this table with your dots. All right, and as you are adding your dots and finishing out this table, you guys did a lot of simulations, so we got some good data to work with. Thanks for that. As you are going through and doing that, anyone can jump in and answer. What would you expect the proportion of females laid off? What would you expect it to be?
Point 0.3.
0.3, yeah. So we know it's 33% female. So we would probably expect somewhere close to 0.3, and that's what we're getting right here. You can see we're definitely hovering around that range. So maybe like this would be the expected value, the expected proportion from that. And you know, the simulation is bearing that out. I'm going to assume everyone's got their, oops, I didn't mean to do that. Gotta keep my stuff in there. Let me just, all right, so that didn't work out. Something went wrong. Okay, so now the next question is, what percentage of the dots represent half or more females being laid off? You can just circle the area. What represents half or more? Okay. So no one's, hopefully you're just identifying it. I'm just going to move forward. There we go. Got our circle right there. So those are the ones that represent half or more. So I was the outlier here with that 0.8. That was very bizarre seeing that. But let's kind of figure out what this percentage is when we break it down. I'm going to count up the dots best I can. I might not get it exact, but that's okay. So I got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29, 30, 31, 32, 33. I counted 33 dots. And out of that, 1, 2, 3, 4, 5, 6 of them were at 50% or higher on females laid off. So if I convert that into the decimal using some advanced mathematics, looks like that's about 18%. So there we are. So I guess the question is, and I think we'll get to this question, so I won't ask it right now. So 18% of our simulations resulted in half or more of them of the 10 being female. Okay. So let's interpret this in context. And I will clear all the drawings real quick. Okay, so assuming the the lottery was fair, this is, I guess, a lottery you don't want to win. There is an 18, we came up with about an 18% chance of 50% or more of those laid off being female. Okay. So I think we have a question to this effect, but really the idea is 18% something that makes you kind of question it if it was fair or not? Just an 18% chance of what happened actually happening. Is that fair or is that unfair? And that's really the key. You have to determine if 18% is unlikely or if it's fairly likely. Okay, so let's see here. Do we have convincing evidence of gender discrimination?
Yes.
Okay, and why do you say yes?
Because that percent is really low, and if there wasn't gender discrimination, then it would be closer to 100% or a proportion of 1 that something like that would happen.
Okay. I'm listening, I'm reasoning through what you just said. If there was not, okay, well, maybe let me see if I can interpret what you're saying, and you can tell me if you meant something different. So if it was just random chance, like we just did with our simulation, it only happened 18% of the time. But if there was gender discrimination, then it would be much more likely, and it's maybe only happening because there is discrimination going on. I don't know if that's what you meant.
Well, if there wasn't gender discrimination, then the percentage would be higher because this is more likely to happen based on the proportions of male and female in the population. But since it's so low, then since it's so low, then that means that there's like less of a chance that it'll actually happen. So therefore there is gender discrimination.
Okay, I think that last phrase there made a lot of sense to me. This is unlikely to happen based on random chance. And I know you're kind of getting to that point. So this is where, you might, and we're going to come up with some statistical standards that we use to determine if something is uncommon enough. Now, if I converted 18% into a fraction, 18% is roughly what fraction? One and what?
1/5.
1/5. It's close to 1/5. 1 in 5 chance. Now, when we put it into that language, does 1 in 5 seem likely or unlikely? And everyone could have a different answer to this, So I'll just say this is more likely than getting a specific number when you roll a die. So getting a 6 on a die is less likely to happen than this outcome is to happen. So you can use that and determine for yourself if you think it's convincing evidence. I will say this as my answer. And we're going to, again, learn some very hard and fast rules that we follow to determine if we have convincing evidence or not. Right now, I'm leaving it up to your subjective determination. So because there is almost a 1 in 5 probability of this happening by chance, I would say we don't have convincing evidence of gender discrimination. All right, I'll just leave it right there for a second. So again, you might agree or disagree with that assessment, but 1 in 5 isn't that unusual. Going back to the 2016 election, of course, this is just an anecdote I think that applies here. There's a website, 538, that kind of has projections on who's going to win the election. And leading up to the 2016 election, I think they had something like a 60, let's say 70% chance. Let's even go 75% chance that Clinton was going to win that election, which when you hear 75% chance of something happening, a lot of times that turns into a 100% chance. But we have to remember, 75% chance is just 3 in 4. So there's a pretty darn good chance that that 1 in 4 is going to be what rolls. And that's what happened. So even a 75% chance of something happening, which seems like almost a sure thing in our head, well, 1 in 4 times it's not going to happen. So just keep in mind, so as you're looking at the new election coming up, I think the most recent probabilities show that Biden has like an 88% chance of winning, just based on current polling, which seems like, oh, Biden's going to win, right? Well, except we don't know, because there's still basically a 1 in 9 chance that Trump could win. And 1 in 9, those are not small odds, okay? So I think I'm using the election here as an example of what is unlikely and what is likely, okay? Sometimes we're not, and this is just a general human thing, sometimes probabilities can throw us for a loop. Okay, what we just did was we tested a hypothesis. And the hypothesis was that firing practices were biased. And we're going to use statistics to investigate this formally. And so we'll kind of jump into exactly how that happens. So in a very real sense, we're figuring out the probability of an observed outcome happening and using that probability to determine if it was a result of random chance or if there was a real difference from what might be expected. So was that 5 out of 10 just a random thing that might have happened, or was it a sign that there was something nefarious going on? Okay, and that's kind of what that last thing said. So when we're testing, we always start with the idea that there's not a difference between what we expect and what actually is going on. And that's called the null hypothesis. So the null hypothesis would be that the proportion of women who are fired is going to be 0.333, which is at 60 out of 180. And that there's basically that's saying that there's not discrimination, that it was a fair process and it would average out to 0.333. We just happen to get 50%. Okay, so that's a null hypothesis. We use H sub naught as when we say that. If the concept is difficult to understand right now, and some of this might be like, what is he talking about today? It will make sense more and more as we go through specific examples. I'm just throwing out some concepts today. Okay, there's no effect from any specific causes. And this is not, I should have changed this phrasing. It's not that there's no effect, but there's no evidence of an effect. Okay, so we don't have evidence of gender discrimination going on. That doesn't mean it's not happening. It's just we don't have evidence from the statistics. Okay, there's the alternative hypothesis, which is that there is some kind of difference between what we observed and what we expect. And our alternative hypothesis was that discrimination was taking place and management was laying off women at a higher than expected rate. So the way that our observed outcome differs from the expected is important. Okay, and what I mean by that is that when we were looking at the proportion of women fired, we were thinking gender discrimination was happening, and so therefore the proportion was higher than the amount that we expected. So it's important to say our alternative hypothesis is that the true proportion is higher than 0.333. And there's some kind of non-random chance reason that that's happening. Okay, we could claim that a proportion will be lower depending on the situation. Now let's say we just don't think that it's the expected outcome. We're not sure if it's going to be higher or lower. We could just say it's not equal. So I could have had an alternative hypothesis that said, well, I don't know what the proportion is going to be, but I don't think it's going to be 0.333. And I think it's going to be different somehow. And that could have been an option, but not in this case. We were thinking that it was higher. Okay. So again, this might not completely click for you today, but it will make sense as we go through quite a few examples over the next few weeks. Okay, so the hypothesis test is always testing the null hypothesis. And when we are done with our calculations, we can either reject the null hypothesis or fail to reject the null hypothesis. Okay, and those are the only things. We never accept or accept the null. We never accept a hypothesis. We either reject the null or fail to reject the null. And it's just this verbiage right here that is kind of keeping things, I think you could probably understand why we're doing this, but we don't want to make a definitive statement. All this is probabilistically speaking. We do have evidence that suggests that discrimination is happening. So we're going to reject the null hypothesis that this was a fair process. Or we fail to reject the null. We don't have enough evidence to say that gender discrimination was happening, so we don't reject the null hypothesis. But we're not saying one of these is true or false. Okay. And so here's in our example what we might say. Our null hypothesis is that the true proportion, it was a fair process, and we would expect about 33% of those laid off to be female. The alternative hypothesis is that it's going to be greater than 33% because discrimination is happening. Okay, so hopefully you're following along with this so far. And now we jump into some other really important concepts. And this one is one you might have already come into this class having heard of before, and now you get to learn all about it. The p-value. Anyone already familiar with p-values? Maybe you've seen it in some papers you read for other classes and stuff like that. I don't know. The p-value is the probability of obtaining a value as extreme as the observed one on the condition that the null hypothesis is true. Now, we did this. We did a simulation, and in our example, the p-value was the probability of having a proportion of women among those laid off at 50% or more, given that women are laid off at the rate of 33%. And we set up our scenario so that it was a 1 in 3 chance of being a woman laid off, and then a 2 in 3 chance that it was a male laid off. And we found that we still had an 18% chance of getting the result of 50% or more. So we set it up in a fair way. Okay, so if you're following along with that, let's see what else happens. The p-value is the area under the normal curve that we'd expect. So it is a solution to a normal CDF calculation. We're not doing those today, but we will do that tomorrow. And now we get to the last important concept, and I'm going to be reinforcing what a p-value is over and over again, and we'll see what that means in specific context. So how do we decide if a change is significant or not? So we need to decide that before we even begin our calculations. We have to decide how unusual an outcome should be before we decide that it can't be explained by random chance. So before I go any further, what's maybe a significance level that would make you kind of doubt that it was random chance that made it happen? So if something has like a 1 in 2 chance of happening and it happened, would you be skeptical of that? Would you say, I think that might have been some discrimination or something else going on? Or would you say, oh, that's random chance? It's 50-50.
It's random.
Yeah, I think 1 and 2 is the definition of random. So yeah, I mean, it could happen, it could not. It's 50-50. So 1 and 2, I think we're safe to say, I'll just keep track of this. 1 and 2, okay, that's not very unusual. What about 1 and 4? Would that seem unusual to you?
Not too unusual.
Yeah, I mean, it happens 25% of the time. I think it's fair to say if something has only a 25% chance of happening and it happens, you'd say, oh, okay, is that 1 in 4 time? So you can kind of determine, here, we'll do something that's kind of different. So how unusual, and you can treat this like it's a, what's the word I'm looking for? Continuum, okay? And you can just put a dot somewhere. Where does it become so unusual that you're like, I think that random chance wasn't the result, wasn't the cause of this? Where do you feel comfortable kind of putting the dot to say, now it is not random chance? Okay. All right, we got a few different opinions on this, but they're all hovering around the same area. Anyone else? Now, I will say that this came up in 5th hour. Someone was like, well, isn't it situation dependent, you know? And to that, I'd say absolutely it is. Because a 1 in 20 chance is not likely, but if those were your odds to win the lottery, you would jump at those chances. You would buy 1,000 tickets at that price if you had a 1 in 20 chance, because you know you're going to win a big jackpot, and so that 1 in 1,000 doesn't matter. That $1,000 you spend doesn't matter. But if it was only a 1 in 20 chance of getting a question right on a test, then you're like, well, that's just an incredibly hard question. Those odds are not, those are too difficult of an odds. So something is going on here. Maybe we didn't cover that material. Anyway, so it's situation dependent. We can see it hovers around 1 in 20. So, okay. This is what we call our significance level. And we kind of set this arbitrary value at the beginning. We say, if the probability of this happening is less than a certain amount, then we're going to say it's unlikely enough for us to reject the null hypothesis. Okay. So we might suggest there's evidence that some other causes played a role. Okay. So I will clear this, and we will look at statistically the values we use. And some of you might have already seen what the common values are, and we're going to see those now. So frequent significant levels are 0.05 and 0.01. So basically a 1 in 20 chance, which is where a lot of you kind of put your dots, and then a 1 in 100 chance. And it depends on the situation which one we want to use. So we can put this into context. Now, these are called alpha levels also, but an alpha level and a significance level is the same thing. It's just there's two different terms. We use the alpha symbol, which is basically an A, to set the significance level. Okay, a significance level of 0.01 means that we would need a probability of 1% or less in order to decide that the result is unlikely to occur by chance. And let's look at that initial activity. Let's say instead of 5 women laid off, there was 9. Now, no one got that. And looking at this, it's approximately this value. I didn't get an exact probability, but the probability of 9 or more women being laid off, if it was a truly random process, is 0.00035556. So 0.04 chance of that happening. So if that happened, then I would say, oh my gosh, there's no way that happened by chance. Very, very unlikely. So I think some discrimination took place. So this would be convincing evidence that the process was unlikely to be fair. So we would reject the null hypothesis. And our null hypothesis was that it was a fair process. Okay. Hopefully this is all making sense. I'm not confusing you guys with anything. So let's just go through a quick example here and then we'll call it a day. We're not having to do any math with this. This is all interpretation. So calcium is a vital nutrient for healthy bones and teeth. The National Institutes of Health recommends a calcium intake of 1,300 milligrams per day for teenagers. The NIH is concerned that teenagers are not getting enough calcium on average. Is this true? State appropriate hypotheses for performing a significance test. Be sure to define the parameter of interest. Okay, so let's start with defining the parameter of interest. The parameter of interest is the average, the true population mean, and it's the true population mean of mean daily intake of calcium for teens. And I'll just put in milligrams right here. Technically it's milligrams per day, but we're good. Okay. Now we have two hypotheses. We've got H sub naught and we've got H sub A, the alternative hypothesis. Now, our null hypothesis is that everything is exactly the way it should be, and that the mean truly is equal to 1,300 milligrams per day. Now, the alternative hypothesis, the NIH is concerned that teenagers are not getting enough calcium. So what they're concerned about isn't that they're getting too much calcium or they're just getting not 1,300 per day, but they're concerned that they're getting less than 1,300 milligrams per day. So that's what we're really testing right here. Okay, so are there any questions on this so far? Okay, and I'll tell you that your homework tonight is going to be looking at more examples like this. So we're going through basically a homework type problem for tonight. Okay, so that's kind of, we set up our two hypotheses. I'll clear that. So researchers did a test. They studied 20 teens and they looked at it, and basically when you get down to it, their sample mean was 1198 and the sample standard deviation was 411, and they got a p-value of 0.1404. Okay, so what would it mean for the null hypothesis to be true? Okay, so if our null hypothesis, which again is that the mean is equal to 1,300 milligrams per day, is true, then we would say that the mean daily intake of calcium for teens is 1,300 milligrams. So it's kind of restating the null hypothesis just in everyday language. Okay, but now the p-value. We need to interpret the p-value. And remember, the p-value is the probability of getting the results we did on the assumption that the null hypothesis is true. So assuming that teens are getting 1,300 milligrams per day of calcium, there is a 14.04% chance of getting a sample mean of 1198 or lower. Okay. So that is how we can interpret the p-value. All right, so now we would decide if our significance level, or alpha, was 0.05, what conclusion do we make? And of course, you can kind of work through that, but here's how we might phrase this. Because the p-value, and I'll go ahead and say that's because the p-value of 0.1404 is greater than our alpha level of 0.05, because it's greater, we fail to reject the null hypothesis. And what we're really saying here is we don't have convincing evidence that teens are getting less than 1,300 milligrams per day of calcium. Okay, so if you forget kind of the phrasing and how you should be approaching these problems, this is now up here on the video for you guys to come back to and refer to. So even though, yeah, we were 100 milligrams below in our sample, there's still a 14% chance of that happening by random chance, just because the 20 teens that were picked out happened to have slightly lower intakes. But we could have gotten a different sample that they got over 1,300. So this could have happened by random chance. And because our significance level was set at 0.05, we are looking for something that happened that has a less than 5% chance of occurring. This does not, we don't reject the null hypothesis. Okay, and again, hopefully just conceptually you can wrap your head around what we're talking about today, but we are not done seeing this kind of stuff, not by a long shot. So we will continue to work through specific problems, including the calculations. So what I want you guys to do tonight is read chapter 20 if you haven't already done so. On the Canvas page, I posted, in fact, I'm gonna get out of this real quick and go over to the Canvas page for today. I posted a few videos. These are some good overview videos on tests of significance and inference for proportions. So you're gonna see some stuff as heads up based on what that we're gonna be doing tomorrow. This other video is on confidence intervals, just as a way of wrapping that up. And for your homework, I posted a PDF of a worksheet that just has a couple of problems, and so you can work on that tonight. Okay, so that's really all I've got for you today. If you are good to go, you can have a wonderful day. If you have any questions, you can stick around, but have yourself a wonderful day.